Okay, in this presentation we are going to look at the Lomax distribution. This is also known as the Pareto type 2 distribution, and that is a heavy-tailed probability distribution that is commonly used in business, economics, actuarial science, queuing theory, and internet traffic modeling. Okay, so it is essentially a Pareto distribution that has been shifted so that its support begins at 0. By the way, this is all from Wikipedia. Just as a remark, it is named after K.S. Lomax. Now, what we're going to do here is create an algorithm that generates a sample drawn from the Lomax distribution. Okay, so we're going to use the inverse transform sampling method with Julia. So just in the first instance, I have some packages there ready, statistics, distributions, and random, and I'm going to have them sort of on standby almost permanently for these probability distribution presentations. Now, I'm going to talk a little bit about the theory. Parameters are alpha and lambda, the shape parameter and the scale parameter. The support is x greater than or equal to 0. Now, so there's a couple of other things there, but essentially the key thing we're actually interested in is a cumulative distribution function, okay, CDF, and that is 1 minus this expression here. So in brackets we have 1 plus x over lambda, and that in brackets we have that to the power of minus alpha. Okay, so 1 minus that. Okay, so essentially the part in the brackets is the survival function with, of course, that minus alpha power there. Okay, now, so what we're going to do is start off with the cumulative distribution function. So that is that expression there. Now, the cumulative distribution function, f of x, takes some value in the interval 0 to 1. So we can simulate that with a uniform deviate u. So this is a number drawn from the uniform distribution. Okay, so we're going to let that equal the CDF, the cumulative distribution function, which in turn is equal to 1 minus 1 plus x over lambda to the power of minus alpha. Okay, so if we rearrange that algebraically, we get 1 minus u equals 1 plus x over lambda to the power of minus alpha. Okay, now this is important in the context of inverse transform sampling and all this sort of modeling of random processes and how to generate them. So because u and 1 minus u are essentially the same random variable, we can interchange them when necessary if it simplifies the algorithm. So what I'm going to do is replace 1 minus u with u without any loss of generality. It doesn't affect the algorithm at all because 1 minus u and u essentially are the same process when we draw a random number from the uniform distribution. So we have u is equal to 1 plus x over lambda to the power of minus alpha. So what we can do here is put both sides to the power of minus 1 over alpha. Okay, so that just gets rid of that minus alpha there. So essentially what we want is plus 1 on that side of the equation on the right hand side. Okay, so u to the power of minus 1 over alpha is equal to 1 plus x over lambda. Subtract 1 from both sides and multiply by lambda. Okay, so we end up with x equals lambda to the times u to the power of minus 1 over alpha minus 1. Okay, now essentially that is the what we're asked to generate. So essentially what we have to do now is implement that with Julia. So I'm going to set up n equals 100,000. I'm going to arbitrarily set alpha to 3 and lambda to 4. Okay, so here we go. U is n random numbers drawn from the uniform distribution. Okay, so u to the power of minus 1 over alpha. Now just remember that dot there to signify element-wise operations. Then I have minus 1 here. Okay, and again the dot there, the dot minus 1, so 1 is subtracted from each of the resultant values. And then I pre-multiply that, or I post-multiply it by lambda. And that gives me my algorithm. So if I was to run that there, I've set alpha equal to 3 and lambda equal to 4. If I was to run that there and get x, that's what we would get. Now, I'm going to see what I have here. I'm just going to sort of put in a cell here and see what we have. Just run that and see what we get. Now, this should be 100,000 observations from the Pareto type 2 distribution, the Lomax distribution. How do we know if we have done a good job? Okay, well, let's look at some analytical results and compare them to our sample. So for the mean of the Pareto type 2 distribution, the Lomax distribution, the mean should be lambda divided by alpha minus 1 for alpha greater than 1. It's undefined otherwise. Okay. Now in this case, for alpha equal 3, and which we note is greater than 1. Okay, so this is the correct definition of the mean to use. And lambda equal 4, the analytical mean should equal to 2, which is 4 divided by 3 minus 1, which is equal to 2. So let's see how close this is with our sample. So let's run that. 1.99, very close. Now, let's see what the median is. So the analytical value of the median is equal to lambda times the alpha root of 2, okay, minus 1. So in this expression in brackets. So this is 2 to the power of 1 over alpha. And then we subtract 1 from that and multiply the whole thing by lambda. Okay. Now the analytical mean should equal to 1.0396. This is how we would sort of set that up there. We have no vectors there or arrays or anything like that. So this is straightforward scalar multiplication, scalar operations, 1.306. Let's see what our sample value is. 1.3097. Good enough. Finally, the quantile. This is the quantile function of the Pareto type 2 distribution, the Lomax distribution. Okay. So what I'm going to do there is set up a series of quantiles for 10%, 25%, 50%, which is actually the median, which we've already done, 0.75 and 0.90. So if the theoretical quantiles and the sample quantiles match up, I think we'll sort of think we've done a good job. So 1 minus p, I'm going to do this in chunks. So I'm going to initially set that up in terms of quantiles, okay? And 1 minus the quantiles, so it's 1 minus p, to the power of minus 1 over alpha. Okay, so that's the power of minus 1 over alpha. And again, you notice the little dots there because element-wise calculations, because we're dealing with an array here. Okay, and then multiply that by, subtract 1 from that, and then multiply the whole thing by lambda. Okay, so let's have a look at that. And so that's the theoretical quantiles there. And let's see what the sample quantiles work out to be. Let's run that. So 0.143, compare that to 0.1429. 0.422, 0.22, that's compared to 0.4025. We know that the median is pretty good, 1.0397 compared to 1.0396, 2.341 compared to 2.349, close enough, and 4.580 compared to 4.611. Yeah, so there's a pretty good matchup there between the theoretical quantiles and the sample quantiles from our sample of 100,000 values. So I think we've done a pretty good job at simulating the Lomax distribution using inverse transform sampling. So we set up this little algorithm there, and to finish off, we'll just go back to this algorithm. Now, it's very petite actually, it's not a whole lot to it. Really, the whole process really was involved here in this setting it up, this process here. That's where all the hard work was done. Okay, we'll leave it there.